Define manufacturing methods. In this video, we'll set up generative design manufacturing methods. In Fusion 360, we want to carry on with our generative suspension design. If we take a look in the browser, you can see that we have our preserve and our obstacle geometry set up. We have our symmetry plane set up. We've defined our objective to maximize the stiffness, and our limits are going to be our safety factor of 2 and the mass target of 4.5 kilograms or 10 pounds. The next thing that we want to talk about is our manufacturing methods. And by default, unrestricted, additive, and milling will be on. But these are not always applicable for our designs. So let's explore those manufacturing methods by going to our design criteria and selecting manufacturing. On the right-hand side in our manufacturing dialog, let's take a look at all of our options. First, at the very top, we have cost estimation. This can be extremely handy if you have a specific manufacturing method in mind. For example, additive, milling, or casting can be extremely helpful to have costing data. For the purposes of our example, we're going to turn off cost estimation. We will get a warning inside of our pre-check that tells us that our part is likely too large for a specific material, or if we have cost estimation turned on and we have an unsupported material, then we'll get a warning there as well. The next method down is unrestricted. Now, the unrestricted method is typically something that we would see in a higher performance application where we're really looking at understanding without any constraints what the ideal design looks like. Unrestricted can still be manufactured, but you are not holding it to any of those manufacturing constraints. I typically will include unrestricted in any study that I'm solving just to get a good idea of what an unrestricted or an under-constrained model is going to look like. Now, it is important that we understand in this design process that each time we select a manufacturing method, it's going to give us additional outcomes to review. The unrestricted is going to give us a single unrestricted outcome for each material we select. When we move on to an additive, then it's going to give us an outcome for each material and each orientation. You'll notice that right now, by default, it has Z plus as the orientation. This would be how you set the part up to be 3D printed. If you want to include all orientations, you can easily do that by selecting a checkbox, and then you need to define things like the overhang angle or the minimum thickness. These values, of course, are going to be machine specific. So if you don't understand what these values mean, then it's important that you research the type of machine that you're using and figure out if they have any overhang issues and whether or not there's a minimum thickness that you want to adhere to. When we're talking about overhang, this is typically what we're going to see when a part is building vertically, how much it can actually build outward each pass without having to have additional support material. So you can see in the tooltip that we have a 45-degree overhang angle, which allows the bottom face that's being printed in that orientation to actually build without support material. If you have a specific machine that has that requirement, make sure that you do enter it. But for our example, we're going to turn off additive. The next option is milling. And under milling, we have 3 separate configurations that we can choose: 2.5 axis, 3 axis, or 5 axis. These are going to determine the tool orientation and the axis that it has to actually machine and create our geometry. When we have a 5-axis part, this means that the tool can tilt and move around to get the tool into certain areas and machine that geometry. This is going to give us the best result in terms of being closer to an unrestricted design. But keep in mind that if your intention is to actually mill this part, then you want to understand what your restrictions are. For our specific part, this is going to be extremely difficult because we have holes in 3 separate directions. The ball joint is in the Z plus orientation, the lower shock mount is in the Y, and the mounting that attaches to the car is in X. This means that in order to machine all of this geometry, a tool would have to come from 3 different directions. When we set up a configuration for 2.5 axis or 3 axis, we can set up the tool directions. When we use this, we can include all 6 directions, allowing the tool to come from those different directions. But again, it is going to be assigned based on our coordinate system. For our example, we're not going to be looking at milling, and we're not going to be looking at two-axis cutting. Two-axis cutting has some additional requirements that we should understand, though. Whenever we're setting up a design for a two-axis method, all of the preserved geometries need to be at the same height. It's assuming that we're cutting this out of a single sheet of material, and when we're using something like a laser or a water jet machine, these are all going to take a flat sheet of material and cut the part out. So in order to qualify for two-axis cutting, all of our preserves need to be at the same height, and obviously we have some geometry that just would not work for two-axis cutting. The last method that we have here is die casting. Now, die casting is a great option for suspension geometry, and keeping in mind that we can post-process these parts. With die-cast parts, there is always going to be machining that happens after the fact when you have areas like a taper for a ball joint, or specific areas like a shock mount that must have precision tolerance. When we're looking at die casting, we can pick one or multiple directions for the ejection. In this case, we would be looking at possibly Z, but this means that we would need to have some cores that were in the X and the Y direction as well. When we look at the values that we can dictate, we have draft angle, we have minimum and maximum thickness values. These values are going to, again, be constraints that are placed on the outcomes. We're already looking at maximizing the stiffness with a factor of safety of 2 and a target mass of 10 pounds. It's going to additionally add die casting restrictions, making sure that all the geometry is visible within 3 degrees of the Z pole direction. So these criteria will help give us more outcomes, but it is important that we do understand those constraints or restrictions that we are placing on the solve. For our example, again, we are not going to be solving this, but we're going to use unrestricted and die casting as the most viable methods for manufacturing this part. So we'll select OK, and then we want to make sure that we do save the design before moving on.